Welcome to AI Paperslop. If you are an AI researcher or ML engineer trying to stay up to date, our mission is summarizing AI and tech papers directly for you.
Right, getting straight to the core insights.
Exactly. And today we are jumping straight into a paper called Expanding Flow Maps by Sophia Tang and Pranam Chatterjee from the University of Pennsylvania.
And the immediate technical takeaway you need to know here is that standard flow-based generative models are trapped on a fixed canvas.
Like locked into a predetermined dimensionality or sequence length right at initialization.
Yes, exactly. But this paper completely shatters that constraint. They introduce expanding generative flows, or EFlows, and expanding flow maps, EFMs.
And they do this by factoring the generative process into two learnable operations, right?
Yeah. First, an expand operator that adds conditional noise to organically grow the state. And second, a transport map that pushes this expanded state forward.
Which means the model can generate variable length text, dynamic molecular graphs, and adaptive resolution data in as few as 1 to 4 steps.
Outperforming state-of-the-art multi-step diffusion models.
So if you build or train generative models, this framework fundamentally changes how we handle data, where the output size is a learned, controllable degree of freedom.
I mean, it's a massive shift. We are moving away from just rigid arrays.
Right. But to really appreciate how they did this, we need to look at why standard stochastic interpolants just fail so spectacularly at this task.
Well, if you look at the baseline, standard stochastic interpolants construct a continuous time path between a prior, pure noise and a data distribution.
Usually called $P$ and $P$.
Exactly. But they construct this path on a fixed state space, $2.
Meaning, if your dimension dollars is set to 128, it has to stay 128 from start to finish.
Right. The velocity field expects a 128-dimensional input, and it's hard-coded to spit out a 128-dimensional output.
But in reality, sequence length and dimensions vary, like audio duration, image resolution, or text.
Yeah, you literally can't use a fixed-dimension velocity field to transport a state from a lower dimension, amaragous, to a higher dimension.
The math just physically breaks down.
It does, because mathematically there is no diffeomorphism between spaces of different dimensions.
So EFlows fix this by replacing that fixed dimension dollars with a non-decreasing dimension schedule, DPT.
Precisely.
It's kind of like normally generative models paint on a fixed canvas, but EFlows are like a canvas that physically stretches, weaving new blank threads into itself while the paint is actually being applied.
That's a great way to visualize it. But to make that stretching canvas mathematically sound, we need to know how the model gets from DPS without breaking the continuous flow.
Right, because you can't just magically spawn new dimensions.
No, the ODE would just crash instantly. So that is where the expand operator comes in.
The EPT.
Yeah. Its job is to lift the source state into the target dimensionality by augmenting it with conditional noise.
And the paper actually details 3 specific ways to do this, right? Based on what you're generating.
Right, 3 instantiations. The first is concatenation, which is literally just appending new coordinates to the end.
Which is great for autoregressive text, I'd imagine.
Exactly. The second is positional insertion. Instead of putting them at the end, it interleaves noise at specific gaps.
So, really good for infilling tasks.
You've got it. And the third is child expansion, which attaches new coordinates to a parent state.
Wait. If we use child expansion, that literally generating a skeleton first and then conditionally expanding the state space to add the flesh and skin.
Yes, that is exactly it. It is built for coarse-defined structures, which we'll see with the molecular experiments later.
Oh, wow. Okay, so once it's expanded, then comes the transport map.
Right. Once expanded, the standard velocity field just takes over again. It integrates the continuous time interpolant to denoise the state.
Okay, I follow that. But looking at this, there's a glaring mathematical problem here.
The mixed noise levels.
Yeah. If we are constantly injecting pure noise into a system that is already half denoised, how does the model balance that? The velocity field should just collapse.
Standard diffusion would totally collapse, yes. But they saw this by introducing local time coordinates.
Okay, how does local time fix it?
Well, each inserted component gets its own local clock. So upon insertion, its time starts at exactly $2 and then scales to 1.
Oh, so the model tracks a full vector of local times.
Exactly. So it always knows exactly how noisy every single dimension is. It treats the old dimensions like they are half-baked and the new ones like they are raw noise.
That is incredibly clever. But how do you unify those sudden discrete insertions with the smooth ODE math?
It's all synthesized into a piecewise-deterministic Markov process, or a PDMP.
Ah, PDMP.
Yeah. It combines the expand operator, which acts as the jump or insertion, and the interpolant transport, which is the smooth ODE.
So it's governed by an insertion intensity and a jump kernel.
Right. The insertion intensity dictates when the jump happens, and the jump kernel dictates how the state expands. This is really the secret sauce for ML engineers listening.
Keeping track of local time via a PDMP prevents the velocity field from collapsing.
Exactly. It's theoretically beautiful.
But EFlows require many steps of ODE integration.
Right. They do, which can be slow.
So how do we compress this beautiful math into something computationally cheap for inference?
That's where we transition from EFlows to expanding flow maps, or EFMs.
Right, because an EFM transports between two states in a single learned step.
Yeah, jointly expanding the dimensionality and pushing it forward in time all at once.
But jumping that far in one step requires serious consistency constraints, right? Like the Lagrangian, Eulerian, and semigroup conditions.
Exactly. And usually the Eulerian condition relies heavily on the Jacobian matrix of the flow map.
And for a fixed dimension, that Jacobian is a nice, neat square matrix.
Right. But here, the input and output dimensions are different, so the Jacobian is rectangular.
Which usually breaks everything.
Normally, yes. But they adapt the constraints to work with rectangular Jacobians, proving that EFMs satisfy all three conditions perfectly.
By ensuring the unlifted diagonal velocity is supported on the active block, right?
Yes, meaning the new dimensions don't corrupt the flow of the old ones. And because of that, you can train these via self-distillation from data or by distilling a teacher flow.
Okay, this all makes sense for continuous data. But what about the discrete world?
Like tokens or graph nodes.
Yeah, you can't just have fractional dimensionality for a word in a sentence.
Right, so they use discrete flow maps. They represent discrete data as continuous distributions over a probability simplex.
Using a mean denoiser instead of a velocity field?
Yes. But the really cool part is how they handle the expansion. They use a learned insertion expectation head.
A neural network head that just predicts the insertions.
Yeah, it predicts the exact number of tokens to insert into every single gap based on the context.
Wait, really? So instead of just padding a sequence to a max length, the model dynamically predicts where the gaps are and exactly how many new tokens to inject into them in one shot.
Exactly. And it uses either a Poisson or a binomial distribution to do it, depending on the step budget.
That is wild. Okay, so theory is only as good as its benchmarks. Let's look at how EFMs actually perform against state-of-the-art multi-step models.
Let's start with continuous data, molecular conformers on GOM drugs and QM9.
This is where that child expansion comes in, generating the heavy atom backbone first, then inserting hydrogens.
Right. And EFlow beats multi-step baselines like GeoDiff and MSGEN in just 20 steps.
And EFM pushes this to 1 to 4 steps, right?
Yes. In fact, with a 10-step refiner, they call it EFM plus R. It achieves the single best AMRP metric on GOM drugs.
Beating models that take hundreds of steps. That's huge for compute costs. What about discrete molecular graphs on QM9?
Generating variable nodes and edges, EFlow beats the 100-step defog baseline in Fréchet-Chemnay distance, or FCD.
And it remains highly valid even at 4 steps.
Yeah, but the one-step EFM absolutely crushes the categorical flow map baseline. It hits an FCD of 0.44 versus 2.14.
Oh, wow, it's not even close. What about discrete sequences? Language modeling on LM1B.
EFlow beats the fixed-length FLM model across all step budgets, which is amazing because it's solving a harder variable-length problem.
And EFM at 2 and 4 steps.
It beats distilled diffusion models like Duo and MDLM.
Well, we should be candid with the technical audience here. There was one limitation with text generation, right?
Yeah, the one-step text generation exhibited mode collapse.
Just too complex to map out in one jump.
Exactly. Predicting full-length expansion and applying the flow map over the entire interval in one shot is currently just too difficult for massive vocabularies.
Still, the multi-step and few-step versatility is unprecedented.
It really is.
So, to summarize the paradigm shift here, we are moving from a world where we pre-allocate memory canvases to a world where generative space grows organically.
It's changing the fundamental approach to data dimensions.
And I want to leave you with a final provocative thought to ponder.
Okay, here.
So, based on a tiny nugget in the paper's conclusion, the math behind the PDMP allows for decreasing dimensionality along the interpolant, too.
Oh, right. The math doesn't strictly force it to only go up.
Exactly. So if expanding flow maps allow us to grow data organically, Could researchers listening right now build shrinking flow maps?
Oh, that's an interesting idea.
Right, taking incredibly noisy, massive data sets and compressing them down to their absolute minimal dimensional representations in a single generative step.
That would basically be the ultimate latent compression algorithm.
It really would. Well, thank you for joining this deep dive into the source material.
Yeah, thanks for having me.
We'll see you next time on AI Paper Slot.